So, hi everyone. Today we're going to deal with motion of a line. And you don't want to overthink these. The idea is that we have a line here, just a regular line, a one-dimensional line, right? One-dimensional line, we'll just call this at 0. T is equal to 0. And this dot's gonna go forward or back on the same exact line, okay? We'll go forward or back. It's a one-dimensional line. We're not going up or down. It's just going forward or back. The example is, this is your home, and this is your school, and we're just going back and forth from school on the same road. Okay. So when we graph this, we end up spinning this around, and we say this is t, and this is s for s of t, and we'll look at this as a position. Okay. Where are we on the road right now? Where are we on the road? So as I gain distance, I'm getting farther away from home. This is my home, getting farther away. And guess what? I am coming now back to home. So you have to think of this as this is my home. And let's say this is my school. So as I get farther away, I'm gaining more distance away from home. And then now I'm coming back to home. Are you guys kind of okay with this concept? Right? And the reason why is because we're just really going back and forth on a single line. This isn't x and y. This is time versus the distance I'm away from my original home, okay, which is the distance away from this guy here.
Mr. Coat.
Yep.
So at the peak is when like they turn around and
I'm
go
farthest.
back.
Yeah. So
Okay.
at the peak is my farthest distance away from home, and then from home I get to come back home. From school I get to come back home, and that's what this idea of position is. Now, there's a point along the way where I turned around, like what Jacob said. I turned around. So at what point did I turn around? We'll call that A here. So at point A, I turned around. And what happens to all my positive positions? They start to subtract. And let's look at this from a different point of view. Let's look at this from velocity. So looking at this velocity, I am positive here, right? I'm increasing my velocity, right? Now, what velocity is? It's the slope of the graph. And the slope of the graph is, let's say I'm going really fast. I go to 0, and then I have negative velocity now. Okay? So what I'm trying to explain here is, I was at some speed. I slow down as I get closer to school. When I leave school, I'm going at a slow velocity, and then I'm racing to get home at the end, the finish line. Okay, and you can see here, this is a positive velocity. This is a negative velocity. But why is it considered a negative velocity? Am I really riding my bike backwards? Like I can reverse my car? No, I've just turned around and I'm just riding in the opposite direction. So we consider this a positive direction and a negative direction. So,
could you explain the velocity one again?
Sure. So the idea of this velocity is, because I do this as a kind of a curved surface, like a parabola. So if I say this as the parabola is example is negative, let me think of a problem that would work. I'm just making something up. So let's say x squared plus, not x squared. I'm just take the roots. The roots are 0, and let's say the roots are 8 or something. Roots are 0 and 8. So my factors are 0x minus 8. So my parabola here is x squared minus 8x. Negative. Okay, I want this to be negative, and that's a positive. Okay, so this is my equation. Y is equal to that. If I take the derivative of this, y prime. Oh, that's called s of t. Okay, that's my s of t. I'm going to change it around. S of t is equal to negative t squared plus 8t, right? Okay, so if I plug in 0, FYI, just make sure you that this works. If I plug in 0, my position is 0 right here. I've not gone anywhere. If my position is 8, if I plug in 8 here, 8 and 8, that's negative 64 plus 64. We're back at 0. We're back at home. And then someplace in between, is where our school is. And that's probably going to be 4, right? Okay, when t is equal to 4, we're at school. Now, the thing is, right now, I want you guys to realize that by looking at this equation, we don't know at what time we turned into school. So there's a trick here. We're going to take our derivative here. That will give us velocity. The derivative of position gives us velocity. Why is that? If you remember what derivatives are change, how fast something changes. So how fast something changes, how fast position changes is called velocity. When you're driving a car, you could be at the mall, and how fast does it take you to get from the mall to your house? That's a change of position. We call that velocity. So we just take the derivative. So s prime of t is the same as velocity for us. Let's take the derivative of this. We end up with negative 2t plus 8. At what point do we stop here? If you remember, this is our horizontal tangent line. Negative 2t plus 8 is equal to 0. T is equal to positive 4. I'm going to draw a sign chart for us. At t is equal to 4, our velocity is 0 there. On the left side of 4, like 3, 2, 1, this will give us a positive number. After 4, 5, 6, 7, 8, if I plug in 5 here, if I plug in 5 here, you see that it's going to be negative. So the way for us to understand this is positive means I'm driving away, negative means I'm coming back. Right? Positive is I'm leaving home, negative, I'm all broke now and I'm coming home sadly. Mom, I'm moving back home. So when we're looking at this here, the position here, we left home really fast. We're out of here. We're booking it to school. As we get to school, we are tired and we slow down. Okay? We're at school. All right, I want to go home now. I'm going to start off my bike slowly. And as I get home, I'm super excited because I'm going to get to play my PS5. And then I race to the finish line. So a couple of cool things that we can...
Would the position ever be under the graph? Like on the negative?
Unless you're 6 feet under, not in this case. Because the position, unless if I go behind, if we do have a negative position, that means I went behind my house. Which is something that we could say, right? Because now I'm farther away from school, you could say. Right? I went the wrong direction. So sometimes you can say, Mikey went the wrong direction to school today. So that's a negative value before he decides to turn around and head the right way to school. So that is a possibility, but it's not always very popular to use, especially if we're just on a single number line. But if it is negative, it's because I went the wrong direction. So that is possible. Okay, so a couple things we want to take away from here. As we said before, we didn't know that this was 4, okay, until we took the derivative. And that's a cool thing about the derivative. We can figure out when did you turn around. And that's what we use to describe the motion. When did the particle turn around? Well, it turned around when we went from a positive number to a negative number. It's just like when we were finding maximum minimums. When did you turn around? When did you crest over? And we find those when the velocity is equal to 0. Because you have to stop before you turn around. You guys are starting to drive right now. And if you are driving in the D gear and you all of a sudden hit reverse on your car, oops, that will screw up your car hard, okay? So, or some of you guys are super lazy. You'll go in reverse, and before your car is stopped, you'll just push it to D, and then you'll drive forward, and you feel a weird jerk in your car. That is not good for your car either, folks, okay? So make sure always to stop your car first. And that's what we're looking here. We stopped our vehicle, and because we can find the 0, we can figure out when and if we did turn around. Now, just on the side here, if the graph looks like this, did I turn around? If this is my position, did I turn around? Right? The velocity function would look like this. It would go up, down, and then back up. There is a 0 here, right? There is a 0 here. But did I turn around from a positive to a positive? No, we didn't turn around. Maybe you're running away. Maybe not. No, life sucks. Let's run. Okay? So there is no turnaround. Just because the velocity is 0,
Why is it 0 on the velocity?
because I stop for a moment right here. So this is tangent line is positive, pause, slowing down, stop for a moment, and then I take back off, but still all in the same direction. All in the velocity is positive. So sometimes we could be tricked thinking that we did have a turnaround just because the velocity is 0. Nope. You only turn around if the velocity changes signs from a positive, negative, or a negative to positive. Okay. And then we have one more thing that we can talk about is our acceleration function. Okay. Acceleration is a change of velocity. So acceleration, I can't misspell acceleration, is a change in velocity. So velocity is a change of position, and acceleration is how fast your velocity is changing. And the way we find that is just taking the next derivative. So acceleration is the derivative of velocity, which is the second derivative of position. Okay? Acceleration is the derivative of velocity. What is the change in velocity? Which is the second derivative of position. Now these are all related, and in physics we call this kinematics, and like kinetic energy, like kinematics, the K part is about movement. And if you're taking physics on the college level, you're dealing with these three equations a lot because they're totally related. Your position is related to how fast you're changing, which is velocity, and your acceleration is related to your velocity because of how fast your velocity is changing. Okay? And if I go and take the derivative of this guy here, looking right here, I can take the, sorry, up, not that one, one above that. If I take the derivative of this guy here, let's jump, sorry. The acceleration equation, which is our derivative of velocity, is just -2. Okay, -2. Now, to go back and talk about graphs in general, if you guys remember concavity, concavity was my second derivative. And my second derivative says here that it's going to be negative, always negative, so that's concave down. And just on the side, remember, see, this was a concave down graph. So some fun stuff here. Now, on your homework, it's going to ask you, for instance, questions of find the velocity function. Well, we said if I have the position, I can tell you what the velocity is. So let's go ahead and look at a easy equation here. If I say S of t, so find v of t. Now, the prompts never tell you take the derivative. That's up to you to realize that there's a relationship between the position and the velocity function. Okay, so if I ask you find velocity, well, this is really the derivative of our position function. This is going to be -3 x squared plus 22t. Oh, sorry, that's a t. I was right. X in my brain. And that's it. If I give you any type of equation, if I say S of t is equal to e to the 2x, or 2t, sorry. Now remember, if I write t here, I have to write t as my variable. That's my issue. So the velocity of this equation is e 2t chain rule times 2. And that's a cool relationship. It's that simple. If they ask you what's the velocity, it's just take the derivative. Will the question be that easy? Probably not, because they'll always have you do something with that. They'll have you do something with that. What is acceleration? If I then find a of t, okay, find the acceleration. Well, the acceleration is the derivative, a of t is the derivative of the velocity. They're totally related that way. So we just take the derivative one more time. and we end up with negative 6t plus 22. If I take the derivative of this guy over here, what is the acceleration of e to the 2t? The acceleration function, again, remember, is the velocity, the derivative of velocity. So we take the derivative again. The derivative of this again is 2e to the 2t times 2 again, which is really 4e to the 2t. Okay. Now, a follow-up, an application to this is what we talked about before. When does the particle change directions? Okay. So let's go ahead and take our last problem. S of t is equal to negative t cubed plus 11t squared. Now, when does this particle change directions? And just like us looking for maximum and minimum values with regular polynomials, regular graphs, we have to first find when the velocity is equal to 0. You can't change directions. This isn't Fast and the Furious. You can't change directions till your velocity stops. And then we go from a positive to negative. Now, just on the side, you can't go from a positive to negative without crossing through a little 0 here, right? How do you get from top to bottom? You have to cross through the ice. So let's go ahead and find out when the velocity is equal to 0. We found the derivative already. That's negative 3t squared plus 22t. And then we have to solve this for 0. Solving for 0 doesn't tell us where it changes. It gives us a possibility. Okay, it says, hey, this might be a place. Just like what we call critical points before. Critical points doesn't mean there's a min or max. It just says, hey, this seems a little fishy here. Let's take a further investigation here. So this one is pretty easy. I'm going to take out the t first. Negative 3t plus 22. Factoring out the t. And then we're going to make them both go to 0. So we know we have a 0 at 0. And then do we have a 0 anywhere else? Let's take a look here. We have a 0 at negative 3.
Over 3.
Yeah. And then so it's t is equal to 22 over 3. Okay. Now, just on the side here, I'm going to draw a little number line. And we're going to start off at 0 because the graph is usually going to start off at 0 times 0. We're not going to say where were you beforehand. Before you were born, where were you? And then we're going to say 22 over 3. Now, we're going to test numbers on the right and on the left-hand side here. Oh, sorry. On the right and on the left-hand side. Now, all you have to do, you don't have to do any math really. Looking here, if the number was really big, bigger than, 22.3, wouldn't this be more negative? So we know it's going to be negative on the left, on the right. If this was a little bit less, smaller, well, then 22 would be bigger. So we know it would be positive on the left. So do we have a change of signs at 22 over 3? Yeah, we do. So we do change directions at t is equal to 22 over 3. Are we going to consider time before here? No. Okay. Yeah, you can't say you change directions right at the starting line. I guess unless if you ran the wrong way. Now, this is why learning calculus and application of calculus is actually pretty useful. Because if I told you this was my position, let's say this was GPS, and I was tracking someone using their GPS coordinates, and I was able to graph their position. When did they turn around? Well, mathematically, we can just find out when their velocity changed to 0. From that point, we can test it if they did change around. We don't have to check every single instant, every single second along the graph. We can just solve for 0. That gives us a point of interest. Then we can investigate that point of interest. Right. What else do we want to talk about? we're going to do integration more a little later, and that will allow us to sum up how far we've driven. Right? So we can say here, we have our position of the school, right, at t is equal to 4. Well, how far did we ride to get there? And how far did we ride to get home? We're able to use that using our integrations, which is kind of cool. But we're going to do that over here using our velocity. Let's see, one more thing. What if I give you guys this instead? What if I say v is equal to v is equal to 3t squared minus 28t. Okay, this is my v of t. And I asked you the question, when is the graph moving to the right or to the left? When is the graph moving to the right or to the left? To the right or to the left? Okay. Now, going back to what we were talking about, this particle motion, we're talking about literally just one line. Are you moving to the right or are you moving to the left? Right? We don't mean right, left, meaning turning right or left at the signal light. We just mean on this one-way particle, are we moving to the right side of the line or left side of the line? That's what we're talking about. Are we going forward or backwards? And that's the part that's sometimes a little confusing. But what if I make a left turn? No, the point is that this is always particle motion is referring to just one line. Are you moving to the right of that line or left of that line? Now, how do I know if something is moving to the right of the line? Well, we're gaining position. That means we have a velocity that is positive, greater than 0. How do we know if we're going back? Our velocity is less than 0, is negative, because we're returning, we're losing position, we're losing money on GME. So how do we figure that out from here? Well, one thing is, make sure you know which equation you got. Which equation we got. And in this version here, we didn't get position, so we don't have to take the derivative. We already got the velocity. Okay? But the problem is, sure, we got all the velocities, but at what point do the velocities change? And that's where we have to find the zeros of this. All right, we have to find the zeros of this. So when do we change velocities? Oh, sorry, when do we know we're going positive or negative? We don't, unless if you want to start randomly plugging numbers in here. So the way we do it is we look for our zeros like we said before. When is the velocity going to equal to 0? And then from there we can know if we're going to the right or left. And that's, in a sense, that's like our sign chart. If I know my velocity stopped here, I can tell if it's positive or negative depending on what values we try. Okay, so let's go ahead and find the zeros for this. This one's pretty easy. V of t is equal to t, 3t minus 28. And that's why calculus is really difficult. It's not me solving for 0 is hard. It's not me taking the derivative is hard. It's me trying to answer the question that they're asking me. Because that question isn't just solve for this. It's here's the situation. You have tools. Pick the right tools to solve for it. So when I'm asking you right or left, first we have to realize that that's velocity is positive or negative. Great. I know that this velocity will be positive or negative. But how do I tell when it's going to happen? And that's the application, that it changes when the velocity is 0. So let's look for those critical points. We have zeros at t is equal to 0, and then 3t minus 28, we want u to also equal to 0. So we're looking at 28 over 3 is equal to t. So we have these positions here. Give me 1 second. All right, so let's draw a simple number line here. So t is 0, that's a nice freebie for me. And then we have a 28 over 3. All right, so in this graph, at what point do we end up, and 29 over 3 is, what is that? That's like 9.33, right? Just FYI, 9.33. Okay, so instead of me actually checking at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to figure out when you did change directions, we just know where the 0 is. You stopped here. Why'd you stop? Who'd you stop for? And then we go ahead and test the right and left side. Now, again, instead of me plugging in a number, I'm just going to, you can plug in 10, right? See how 10 is right there? Sure, I can plug in 10. I can plug in 10. But I want you to do this instead. Just look at 3t versus 28. If t got bigger, bigger, and bigger, if t got bigger and bigger and bigger, is that going to eventually be bigger than 28? It'll be positive on the right. And if you did plug in 10, that'd be 30 minus 28 is 2. On the left, if this 3t was smaller, we would have a negative value on my left.
And you don't have to worry about that first t outside of the parentheses. Just 'cause of
It's because it's just 0, right? And
Okay.
we're not going to worry about before time existed. Right? Starting from t is 0. Usually that's where we start. We start as t is 0, moving onward when we start the clock.
What does this prove again?
This helps us find out which direction the particle is moving at what periods of time. So if my velocity was negative, we would say you're moving left. And when were you moving left? We were moving left between t was 0 and okay, t was 0 and t was actually not, you don't need necessarily this inequality, but 28 over 3. Okay, that's when we were moving left. How do I know it was left? Because the velocity was negative. That means we're losing position. Okay, and in this 1D dimension, losing position, that means I'm going backwards. The particle is moving right. Right? Afterwards, and I want to see how I'm going to write this. It's 28 over 3. As t is greater than 28 over 3. Okay. Or we can write it the other way. T is greater than 28 over 3. The particle is moving to the right. Because the velocity is positive. Now, great, we talked about very abstractly when this particle is moving right and to the left. Now, here is the next part of this. Another application point is how fast and in what position were you in? If I told you, sorry, go ahead.
For this, as long are we just looking between the 0 and the 28 over 3, that's basically the direction it's going for now.
Yeah, because at 28 over 3, we know you stopped your car. We know we pause. Now, after and before, now we can say, hey, which direction were you going? I was going in a positive direction after 28 over 3, but I was going in a negative direction before 28 over 3. So I was going left before and right after.
Okay. So basically our answer would have been left.
Left, yeah, left in my first interval of time.
Yeah.
And then from now on, after 28.3, I was going to the right.
Thank you.
Now, how would this graph of position look like? Well, the graph of position would actually, remember how we said we were negative here? So we'd actually have been losing position till about 28 over 3. And then we would have broke through and gain positive position afterwards. Wait, no, sorry, bad. It's muy normal. Bad. Okay, so I was losing position, right? Because velocity was negative, and then at some point, 28 over 3, I changed my mind, and then I started gaining position to the right. That's how we should look at this. So this is my original S of t graph. Sorry about that. Because our velocity was negative, see how this velocity was negative? So we were losing position, we stopped, and then we started gaining position again. But Ms. Go, you're negative. Yes, we were negative. We owed money. So that's why we had to pay back that money before we eventually are good again. Okay. On the particle, let's say this is at 0. I went backwards first, eventually, and then I stopped going backwards, and I turned around going forward. So I started with a negative velocity, I stopped, and then I went from a positive velocity from where I left off. the last thing we're going to cover is the easiest part of this is now we kind of get the idea of where the particle is moving and when are you turning around. Now the simple question is, where were you freaking at? If I say s of t is equal to, let's say, negative 4, the t to the fourth power plus 10 t cubed, and at t is equal to 3, what is your s of t? So s of 3. What is your v of 3? So the idea here is, what is your position at 3 seconds or 3 hours or whatever 3 refers to? What is the velocity there? Well, all we do is just plug it in. Negative 3 to the fourth plus 10 to the 3 cubed, right? The question is, what position were you at? Well, just plug in 3 because that's our t value. And that's going to be negative 81 plus 90, and that's going to be 9, whatever units that is. Wait, is that right? No, I made a mistake probably. Negative 81, 3, 9. Oh, whoops, this is 270, haha, 270. 3 times 3 times 3 is 27. 270. Sorry, basic math. 270, and then we're at 100. 189. Sorry about that. Multiplication, such a problem. Okay. And then the velocity. Well, how do we get from position to velocity? And this, again, this is where the calculus part is not direct. You have to say, okay, how do I get to velocity? Well, that's just the derivative of position. So you actually have to take the derivative yourself. Negative 4 t cubed plus 30 t squared. So we have negative 4, 3 cubed plus 30, 3 squared. Now this is just kind of like a glimpse into like college math and college science. You are given all these tools, but which tools do I use to answer the question that's prompted? And that's always the tough part. Sure, I know how to find the derivative. Sure, I know how to plug it in, but what do I do to get velocity? If you didn't know the relationship between position and velocity, you didn't know that you had to take the derivative, you would never be able to figure out what to do. So v of 3 is equal to, that's 270 times negative 4, and then 9 times, this is actually 9 this time, right? 9 times 30 is 270, and then this gives us, what?
I think
I messed up
you mean
someplace again.
81 instead of 270.
Oh my gosh. Yeah, 81. Did I mess up over here too? 3 times 3 times 3. No, that part was right.
You didn't mess up there.
Okay, what am I doing? 3
It's
times 3.
minus 108 plus 270, and then it's equal to 162.
Thank you. This is 27, right? My goodness, 81. What did I write? Okay, and then, so this is 162. Thank you. I don't know, I can't do basic math. Hi, YouTube. It's okay, only like one person watches this, so that's good. Okay, and that's this idea of it just answering the simple question, what position and what's the velocity? And we do that by just plugging it in now. Okay, now if I ask you a follow-up question, what is the acceleration? Well, we said the acceleration is related to the velocity by just taking another derivative. So this is the derivative of velocity, or if you want, we can say this is the second derivative of position. They're totally related. So you can start from position. I hope you don't, since we have velocity already. So the derivative of velocity is negative 12x squared plus 60x. Oh, dang it. Stupid x's. I meant t's. Negative 12. At least I'm not getting the calculus part wrong. And then we want to figure out what is the, so this is a at t, acceleration. And we're trying to figure out what it is at 3. Negative 12 times 3 squared plus 60 times 3. That's 9 times negative 12 times 9, and that's 180. That's 108. Negative 108 plus 80, 180 is 72. Okay, so acceleration is 72. Okay, that's it.